Hey everybody, let's take a look at a problem. This is a relatively complex, long problem. And why it's long is because we're going to break it down into small parts. So the general problem looks like this. We're going to do a lot with this problem. I've got a mass on a frictionless rod attached to a spring. Now the spring has a constant, in this case of 150 newtons per meter, and an unstretched length of 1.25 meters. What we're going to do is we're going to bring it over here to the right, and then we're going to let go of it. And so we're going to start it off with an initial distance of 3 meters. That's measured from just below this point on the spring. So I drag it all the way over here to a point 3 meters out. I'm going to let go, and of course the spring is going to pull it back. Okay, again, the spring has an unstretched length of 1.25 meters. I've got a mass of 2 kilograms. And so there's a K over M, which is going to be important. That's the spring constant divided by the mass. That's going to have a value of 75 inverse seconds squared. So if I run this and I want to learn the physics behind it, I'm going to find out that the acceleration is equal to 75 inverse seconds squared, right? That's the K over M value. And then I multiply by the positions of arbitrary value X, measured from this distance here, times 1.25 meters times X, that 1.25 meters again, that's the spring constant, or that's the unstretched length of the spring, and then the square root. And this, of course, is based on the Pythagorean theorem, right? The spring is going to have some length that's a combination of this distance and this distance. And that's all brought in here. So what I've got here is I have an acceleration that's a function of X. And we want to solve that problem using Excel, and we're going to solve it using MATLAB. And I'll show you how that's going to come along here in just a minute. So a couple of things we want to look at. We start off with something really basic. Distance equals rate times time. We've known that since about the 6th or 7th grade or earlier. All right, and what that means is how far do you travel depends on your rate, your speed, if you will, and the time you've traveled. So if I'm traveling at 75 miles an hour down the interstate, and I've traveled for 2 hours, I've gone 150 miles. Right, another way we look at that, and we'll learn a lot of this and have learned maybe in some cases in calculus, velocity is the change in position over change in time. Right, so if I traveled 150 miles over 2 hours, that's 75 miles per hour. Right, now that changes. I mean, if I have it on cruise control and there's no hills, I'm going to travel at 75 miles per hour. But if I'm going up and down hills and I don't have it on cruise control and I'm passing cars, I'm going to have a variable velocity. And so if that velocity changes, that what we call the instantaneous velocity then is the derivative of position with respect to time. Right? And you know from calculus, that's the limit as delta t approaches 0 of this delta x over delta t. We're not going to get into that in too much detail. But we really want to concentrate on this. This is the more important thing for us. So delta x is a change in position. So the velocity, bring the delta t over here, velocity times the time increment, change in time, I'm going to call it a time increment here, is the final position minus the initial position. Now I could do that for a time increment of an hour. I can do that for a time increment of 10 seconds. Whatever I choose, the smaller the time increment, the more calculations I have to do. But that's what the computer's for. Okay? So x final minus x initial. Or I can write this as x initial, bringing the x initial over here, plus v times time increment. Now v might be changing. That's going to equal x final. Or arbitrarily, a position, and we're going to assume k is some sort of an integer. So this might be x3, x4, x12, whatever. X sub k plus 1 equals the previous x, right? The previous x plus the previous velocity times delta t. Okay, so that's how I'm going to find the new position. It's based on the old position plus the velocity times the time increment. I can do the same thing with acceleration. Acceleration is the change in velocity over change in time, right? So if I'm traveling at 75 miles per hour, but I push the gas, I'm going faster. A little bit later, I'm going 80 miles per hour. My velocity has changed. I have accelerated. Now we're going to stick with one dimension for now. All right, so the acceleration, as delta t approaches 0, becomes a derivative of velocity with respect to time. Again, I'm going to stick with this part right here is what I'm really interested in. Acceleration times the time increment equals v final minus v initial. Bring the v initial to the other side. V initial plus acceleration times delta t equals v final. Or v sub k plus v sub k times delta t Oh, wait, that's not right. Sorry about that. Make that an A. V sub k plus the acceleration, which I need to know what was the acceleration, times delta t times my time increment, that equals my next velocity. Again, this is k is 1, 2, 3, 4, 5, etc. It could be 0. It's just an integer value. It's a counting number. Right? So v sub 5 is equal to v sub 4 plus the acceleration times delta t. Right? And I probably should put a k subscript there. All right, so we're going to look at that in more detail as we work with this problem in Excel and as we work with it in MATLAB. And we'll also do a flowchart to kind of see how we're going to work with these equations in order to solve this problem. All right, so we'll continue this here in a little bit. All right, let's move on to step 2 or phase 2 of this process where we're calculating where an object being pulled by a spring is going to be. And we're going to take advantage of a flowchart concept. All right, so this is a concept that we use in programming. We always start with, we're going to just use boxes. All right, that's all of the things that you're doing. All of your steps are going to be in boxes. In some cases, they'll be in diamonds, and that's when decisions need to be made. And we're actually going to do that in a little bit, but for right now, let's just stick with the boxes. Okay, so we always have a start and an end. This is the way programming is going to look. Where do I start? Where do I end? The number of boxes is going to vary. All right, so the first thing we need to do is bring in whatever input information we have. So you may recall from the problem, we had some initial position, some initial velocity, the spring constant, the mass, the unstretched length of the spring was in there as well. And then we're going to want to bring in a time increment. We don't know what that time increment is yet. That's what we're supposed to bring all of this information in. So basically, where do we start? This whole top row is the input information, right? That's the information that has to be brought into the calculations. Then what do? We calculate the acceleration, right? Once we know the acceleration, we're going to take that initial acceleration, we're going to multiply it by the time increment here, and we're going to add it to the initial velocity, which we had over here. So the first time we do this, k is equal to 0. All right, and this is going to give us our new velocity. Once we've got this new velocity, we want to calculate where it's at. And so we're going to get a new position. And the new position equals the old position, which in this case is the initial position, plus, now I actually had this as v sub k on the earlier one, but in this case, it's going to be v sub k plus 1. It's going to be the recalculated velocity. Okay, so a lot of this depends on who we calculate first. Do we calculate position first? Do we calculate velocity first? Do we calculate acceleration first? And then who do we calculate second in that case? So in this particular example, we're going to calculate acceleration first and then velocity. Once we calculate velocity, we're going to use that new velocity, right? This is v1. If I started off with v0, I'm going to use that to calculate my new position. Okay? And that's how we're going to make our new position calculation. And then we're going to end this. Now, if I want to repeat this process, I started off with k equal to 0. This is the spring constant k. These are different k's down here. I probably should not have used that, but those are just counters. So this started off at v0, a0, v1. Okay, and then this started off as x0, but now it's x1, v1 and k and x1 here. So those have changed. Now if I did this again, I would use a1, v1, and x1 and calculate a2, v2, and x2. And then I would start again and use a2, v2, x2 and calculate a3, v3, and x3. All right, and I would do that a number of times, and that's a process where we repeat this over and over again. It's going to be these calculations down here that get repeated. This bottom row, the top row is not going to change, but the bottom row is. Okay, the bottom row is going to change. All right, so this would be inside of what we call a loop in programming, and in Excel we just copy and paste it. It's the same idea, and we'll repeat that process however many times we decide to paste. Or if we drag the cells down, we're repeating that process over and over again. So that's what this is all about here. So we're going to learn to do that in Excel, then we're going to do it in MATLAB as well. Okay. you have any questions, leave them in the commentary below. Thank you.